Welcome, dear students, to the next lecture of satellite communication. In this lecture, we are going to discuss on the orbit ranging concepts of the satellites. That means how we can launch a satellite into any particular orbit. And basically, we will see what are the different orbits and how the satellites, what are the phases of launching the satellite in the particular orbit. So, when we launch a satellite, so it is sometimes the satellite can be launched into the respective orbit in different phases. First, we launch the satellite into a orbit. That orbit is called parking orbit. So parking orbit is a circular orbit, but we try to launch the satellite to GSO orbit, which is a geosynchronous orbit. So in order to launch the satellite into geosynchronous orbit, we launch that satellite into multiple phases. The first orbit to which we launch the satellite, that orbit will be parking orbit, which is nearly circular orbit. Then from the parking orbit, the satellite will be launched into another orbit. So that is called geosynchronous transfer orbit, or it is called GTO. Basically, GTO is an elliptical orbit. It's not a circular. Geosynchronous transfer orbit is an elliptical orbit. So I want to tell that this orbit, geosynchronous transfer orbit, it is not the orbit where your satellite is rotating. It is on second phase where in that orbit the satellite will launch. So this is the second orbit. So when we launch the satellite will rotate in a parking orbit. From parking orbit, it will get a additional thrust, and it will go to the next orbit, that is called GTO orbit. So when it gets additional thrust, so by exhausting some fuels, the satellite will be pushes off with a high velocity. So there will be change of velocity happens when the satellite moves one particular velocity to other one particular orbit to other orbit. Okay. Then at GTO orbit, the satellite will be taken go to next orbit, that is called geostationary orbit. Okay, or we can say GSO or GEO orbit. So like this, in order to reach to the final orbit, the satellite will go through multiple phases. So if you see in the diagram, the center represents the Earth, and this gaseous circle represents the parking orbit. Okay, when we launch the satellite, it will rotate in the parking orbit. Now this blue dotted line represents the GTO orbit, which is an elliptical orbit. Now when your satellite is moving in the parking orbit, okay, and at this particular point, okay, which is called as the perigee. If we consider GTO orbit as an elliptical orbit, so this location is called perigee, and this location is called the apogee in GTO orbit. So at perigee, it will gain additional velocity with some thrust. So with additional velocity, the satellite will change its orbit. So from parking orbit to GTO orbit. Okay, so how the satellite will change? Because when the satellite will launch, it will carry with some fuels. Okay, because when your satellite is moving it cannot be immediately be functional until and unless the satellite reaches to its original orbit. The satellite is not functional. Okay, so in order to carry the satellite, the rocket, which is the launcher, it will carry some fuels. So those fuels will be utilized during the journey of the satellite to the orbit. And once the satellite is put into the orbit, then gradually different systems will start functioning. The antennas, the solar panels, and all those electronic equipment will start functioning. And when the solar plate will open, initially all the electronic equipment, they will be inside a box. So they are in on non-functional condition. So when the satellite reaches there in the orbit, then only the solar plate opens and it can collect, it can store energy from the solar or from the sunlight. Okay, but during the journey, we have to uh, carry additional fuels which will be required during the journey. So when at this particular point the satellite is orbiting in the parking orbit, at this point we give an additional thrust. So additional thrust means what will happen? You know that mm, when aeroplane when aeroplane is moving, when the engine starts, it pushes the fuels towards backward direction so that uh, the aeroplane can move in the frontward direction. So the high amount of fuel it will push towards the back. So what will happen? So some fuels have been came out of the satellite, and finally the weight of the satellite will reduce. And as the weight of the satellite will reduce, then the satellite would move at a very high velocity. So that with high velocity, the satellite will change to another uh, orbit that is called geosynchronous transfer orbit. Similarly, if you see the GEO orbit, which is nearly uncircular orbit, okay, I have not completed this orbit. It will go, like this. Like this, the orbit will be extended, which I have not drawn. I have shown up to this only. So at this point, this is called the apogee point. At this point, we have to we know that when the satellite is moving in an elliptical orbit, at perigee, the satellite moves at a very high velocity. At apogee, the satellite moves at a low velocity. Okay, because that we know from the second law of Kepler, the angle swept by the satellite at any two particular time instants is same. That means if whatever the angle swept here or area swept by this angle, the same area will be swept here in apogee for the same time duration that we have discussed in second law of Kepler. So at apogee point, the satellite moves at a low velocity, whereas at perigee point, the satellite will move at a high velocity. So at this point of apogee, again the satellite will give another thrust uh, with so many fuels coming out of the satellite, and there will be a change of velocity. So due to the change of velocity, the satellite will switch its orbit from GTO to GEO. Okay, so by taking an example, we will see that what is the change of velocity when a satellite, first of all, when a satellite is launched and when the satellite is orbiting in the parking orbit, and from parking orbit to GTO orbit, what is the change of velocity? From GTO orbit to GEO orbit, what is the change of velocity that we are going to see. So the orbit raising is done by combination of motors at launcher at the satellite. Okay, it depends on type and capability of launch vehicle. So the satellite injected to parking orbit, which is a nearly circular orbit. Satellite uses perigee maneuver to GTO. As I have shown in that, at the point of perigee, the satellite will change its orbit from parking orbit to GTO orbit, and then apogee maneuver for GTO to GSO orbit. Okay, so these kind of rockets or the motors are called as the space shuttles. So those space shuttles are of different types we are using. So satellite injected to GTO by launcher. Satellite uses apogee maneuver to GSO. That is what we discussed at the point of apogee. Apogee means away from the Earth. So there is a change to the GSO orbit. So there are many space shuttles or rockets are there. So one is called Ariana. So Ariana is the rocket which is used by European countries. GSLV is particularly used in India. GSLV stands for geosynchronous launch vehicle. And similarly, in Russia, uh, they are using Proton. The launch vehicle is called Proton, and this launch vehicle, it will directly put the satellite into GSO orbit. So this launch vehicle, what the Russians are using, so they don't follow different stages like circular orbit, GTO orbit, and then next GSO. Through this stage, it will not pass. It will directly launch. It will directly put the satellite in GSO orbit. You see the satellite. These are not the satellite. These are the launch vehicles. Okay. If you see this particular, the first image, this one, it's a very thin launch vehicle. This one is called satellite launch vehicle. Okay. Uh, And if you see here, this the satellite launch vehicle, it has some other compartments where we can carry some other payloads like fuels and all we are carrying with the satellite. So this one we called as the um, augmented satellite launch vehicle. So this one, the first one is called satellite launch vehicle, and the higher version of that is called augmented satellite launch vehicle. Okay, then we have improved to another launch vehicle that is called PSLV. So PSLV stands for Polar Satellite Launch Vehicle. If you have a look on all the rockets or all the launch vehicles, uh, your satellite is only this portion. Okay, your satellite, only the white portion is the satellite, and rest of portions are not the satellite. Those are the part of launch vehicle. Okay, so these are different stages. We can call this as one stage. This is another stage. This white portion is another stage. This red portion is another stage. Again, this white portion and red portions. These are different successive stages. So what happens when your satellite will be launched? Okay, so particularly if you have might have observed in DD National, if ISRO is launching any satellite, it will be broadcasted in DD National. Okay. So if you see when the satellite launches in different stages, that means first of all, why multiple stages are involved? Why the rocket or why the launch vehicle is having different stages? The answer is when the satellite is moving from one particular orbit to another particular orbit, there is a change in velocity. Okay, and during the journey of the satellite to the final orbit, we are using the fuel. The fuel will be given from the ground station. Okay, the fuel will be sent with the rocket. So once some portion of the fuel, assume some portion of the fuel is empty, so that part will be removed. Okay, so when the satellite is moving from one stage to other stage, so stage by stage, when the satellite is moving, some portions or some part of the satellite, they complete their functionality by that. So some part of the satellite, they have the functionality from this stage to this stage. Some other part, they have the functionality from this stage to this stage. So every part of the rocket is having their functionality in different stages, and once their functionality will be over, that particular part will be removed from the satellite. Okay, so gradually at the end, that part will be removed from the rocket, not the satellite. So at the end stage, that is the final orbit of the satellite, you will find only the satellite and you will not find the rocket. The rocket will already collapsed. Okay, so the rocket, that means we are investing so much fund in building a rocket. Okay, launch vehicle. We are investing so much, some crores of rupees in building a launch vehicle. But to launch one satellite, we need one rocket. So once the launching is over, the job of rocket is over, and we cannot reuse the rocket further. That is the biggest drawback of satellite communication. And we also have discussed yesterday that the initial investment of satellite communication is very high in comparison to other. Okay, so what is the answer to multiple stages? Because one stage by stages, the functionality of each electronic part of the rocket will be over, and those parts will automatically be removed from the rocket, so that gradually the weight of the rocket will be lighter. So as the rocket weight will be as lighter, as the velocity of the rocket will be higher. Okay, so that additional velocity what the rocket is gaining, that additional velocity is required for change in the satellite orbit. As I had shown here, when the satellite is changing from parking orbit to GT orbit, so there is a change in velocity. Similarly, when there is a change of orbit from GTO to GEO, there is a change in velocity. So that additional velocity comes from where? It comes from all the parts which are removed from the satellite. Getting the point? So then we have another satellite that is called GSLV. So GSLV stands for geosynchronous launch vehicle. Okay, and finally, if you see, this is another version of GSLV. Correct. So it stands for geosynchronous launch vehicle. And now also I will tell you, ISRO is much advanced to put the satellite directly into the geostationary orbit, particularly this GSLV rockets or GSLV launch vehicles. Okay, so this is the question. Why multiple stage launchers? Okay, so answer is this, Delvi. The Delvi stands for the incremental velocity. Delvis represents the incremental velocity. So what is the how the incremental velocity can be represented? That is equal to Vg. Vg stands for exhaust velocity of gas. Okay, how much when we are launching the satellite, so the energy we are getting from the fuels, and that fuel energy will be utilized by the satellite, and the satellite will uh, exhaust some gas with high velocity. That is what happens in also aeroplane. In aeroplane also, the gases will be exhausted with a very high velocity, with a high thrust. It will be exhausted from backward direction so that the aeroplane will move forward. So that is the velocity at which the gases are moving backward. Then natural logarithm of 1 divided by 1 minus mf by m0. What is mf here? It is the mass of expelled fuel. How much liquid fuel, how much mass of liquid fuel is expelled from the satellite. So it is that mass. And M0 stands for mass of launch vehicle, including satellite. So M0 is the mass of launch vehicle, including satellite. That means it is the total mass, the total mass of the rocket. Okay, and how we can calculate the final velocity? Final velocity is the sum of incremental velocity of the satellite. Getting my point? Now, if you observe this expression, when the satellite is launched in multiple phases, okay, so suppose this is the exhaust of velocity of the gas which are existing. Look at this particular parameter. What it is? mf. Mf is mass of expelled fuel. Okay. And in the denominator, m0, it is mass of launch vehicle. But I said that as the satellite is launched through multiple phases, some of the functionalities of the satellite is over, and those components or those parts whose functionalities are completed, those particular parts will be removed from the satellite. By that process, gradually the weight of the rocket or the mass of the rocket or the launch vehicle will gradually decrease. Hence, the value of m0, it will decrease stage by stage. Okay, look at the numerator as well. It is what? Mass of expelled fuel. When we launch the satellite, the rocket carries some fuel, and those fuels will be utilized during the journey. So the mass of fuels will also be, this is not mass of fuel, mass of expelled fuels. So that will be also increasing. So in general, this ratio will be increased. Okay, so finally, if we calculate, the value of del V will increase. So as the del V or the incremental velocity will increase, the satellite will change from one orbit to the next orbit. So what happens when a satellite want to change the orbit? It has to give some additional thrust. So from where it will give additional thrust? By expelling some exhausted, by expelling some fuels, the satellite will change its velocity and change its orbit. Getting the point? So this is what I have explained. In order to maximize del V, that means in order to increase the change in velocity, reduce m0. That is what we had seen. I told you that m0, what is m0? It is the mass of launch vehicle, which is reducing stage by stage or not, because the parts of the satellite will be removed. So as the parts of the satellite will remove, the total weight of the satellite also reduce. So that is the objective. In multi-stage launch, each stage provides a thrust and the dead mass. That is what we are talking. What do you mean by dead mass? Dead mass means the mass of the electronic component whose functionality is over. So those electronic component will be removed out of the rocket. So those are called as the dead mass. So of the emptied container, okay, is removed to reduce m0. Getting my point? Because those components or those parts or electronic parts, they will be removed to reduce m0. Thus, succeeding stages need lower thrust to achieve del V. Now, as the weight of the satellite is reducing by stage to stage, we need less amount of fuel to achieve a particular velocity or incremental velocity, that is del V. So final velocity of the satellite is the summation of all velocity or all incremental velocity, rather I will say. Okay, so at this point, I will have a question to you that when the satellite is not launched, what is the velocity of the satellite? Even every object on the surface of the earth, they are not stationary, they are moving with some velocity. I am also moving with some velocity, and that is nothing but the velocity at which the earth is rotating around itself. So that is my velocity, that is the velocity of every object, every idle object on the surface of the earth. So how we can calculate? We can calculate the total circumference, that is 2 pi r, divided by at what what is the time taken by the earth to complete 360-degree rotation. So that we represent as a sidereal day, so which is about 23 hours 56 minutes and 4 seconds. So if you convert this 23 hour 56 minutes and 4 seconds in term of second, so that is the time duration our earth takes to complete 360-degree rotation. So you divide 2 pi r by this time, then you will get at what velocity the earth is rotating. Okay, so every object, every stationary object on the surface of earth is moving at that velocity. Look at this image. I have shown a globe. Okay, and on the globe, I have some different space organization. You can see ISRO, NASA, ESA. ISRO is Indian Space Organization. ESA is the European Space Agency. NASA is American Space Agency. And yeah, so you see in this image, can you tell me what is the basic common thing? Okay, so you see this particular point, I have colored it in green color. This one is the green color. This one is also green color. So these I have represented the launching pad of the satellite. So in India, we are launching at where? In Andhra Pradesh, Sriharikota. Okay, Satish Dhawan Space Center is there. So from Sriharikota, we are launching the satellites. And NASA, NASA, they are launching in Cape Canaveral. That is the launch pad of NASA. And European Space Agency, they are launching from Kourou. Okay, and even if you go to Russia, they are launching from a place that is called Baikonur. So that is the launching pad of the Russian Space Organization. So what is the commonality? Means how we can decide at what point we should launch the satellite? Why we are launching the satellite at Sriharikota? Why ISRO is launching from Sriharikota? There are multiple places in India there. Even New Delhi is the capital of India. Why we are not launching from New Delhi? Why? And Mumbai is the economic city of India. So why we are not launching from Mumbai or Nagpur or anywhere? But why we have selected Sriharikota as the launch pad of Indian satellites? Similarly, if you see, NASA has considered Cape Canaveral as the launch pad, and Kourou is selected by ESA. So why they have selected that particular point to launch the satellite? The answer is whatever the position we select, the position or the location should be near the sea level. That is the point number one. It should be near sea level. Then question comes, even Mumbai is near sea level, seashore. So why we have considered east of India's, like Andhra Pradesh, Sriharikota, why you have considered? Again, the answer is the satellites are launched in eastward direction. When we launch the satellite, we launch towards east. Okay, so Sriharikota is a position which is located east side of the Indian geographical land. Similarly, if you notice, the NASA, they have selected Cape Canaveral and Korur, all are towards the eastern side of the geographical land, which is near sea level. So this launch pad should be near sea level as well as towards eastward direction. But if you look for Russia, their launch pad is not near sea level. That launch pad is in the desert. That is called Baikonur. Baikonur is a desert area, so they are launching from that area. Then why it is so? Means why we are launching near the seashore or near the seaside? Again, the answer is when we are launching the satellite in different stages, the dead mass of the satellite will be removed. Dead mass means what? The electronic parts whose functionality is over, those parts will be removed from the satellites. So what those parts will do? They will fall. They will fall on the ground surface. Okay. So if we select near the sea level and we launch, so those dead masses will fall on the sea. It will not fall on any residential area. It will not fall any commercial areas. Okay, because it will damage the infrastructure and it will damage the many lives there. That's why we are considering near sea level, so that the dead masses will fall on the sea. So nobody will be harmed with that. So that is the reason. And Russia, they have selected one desert. So nobody is staying in the desert. So any dead mass will fall, any rejected part of the satellite, if it will fall, then it will fall on the desert area. Okay, so no harm will happen to anything else. So this is the answer that why the satellite launch pad is always near the sea level. Okay, so next question which I have, why we are launching the satellite towards east direction? Why not west direction? Okay, that means why Sriharikota? Because the launch pad should be near sea level. Then I asked why not Mumbai? Mumbai is near sea level. Why it is Sriharikota? The answer is since we are launching the satellite towards eastward direction, that's why we have selected a place which is eastern side of uh, geographical land. So all the launch pads, if you see NASA's launch pad is east of uh, America. Europeans, their launch pad is towards east of this South America. So on you can see even India's also. Why we are launching? It is towards east because we are launching towards eastern direction. Okay, if we select a launch pad over here, and from this point to this point, it will take some additional fuel to reach at this point. I am talking about in space, not on the geographical land, because your satellite will not travel on the road. When you are launching in the space, the satellite will take some time. Imagine that when we are traveling by flight, so you take this point to this point. Okay, your flight will consume some energy, some fuel. So it is better to select this place so that this much fuel will be saved. And why? So that is the reason we are selecting in eastern direction of the geographical land. Hope I am clear to the question. Now, next question is why satellite is launched towards eastward direction? Why not westward direction or any other direction? Why we are launching towards east? What is the reason? We know, as just 5-10 minutes before I said, the Earth rotates from from west to east. So the rotation of the Earth is eastward direction. Okay, so even if I am a stationary object, I am not moving. Still also I am moving in eastward direction at a velocity that is equal to the velocity of Earth. That means my position is not stationary. I am also moving. At what velocity? At the velocity of Earth, I am also moving. In which direction I am moving? I am moving in a direction towards east because Earth rotates from west to east. Okay. So if any stationary object, being me also, being my laptop also, or being my house also, all of us, we are moving at a velocity equal to the velocity of the Earth in a direction towards east. That is for sure. Even if we are not moving, if we are stationary, we are moving that velocity. Okay, so by default, I am moving at that velocity. So even if the satellite is not launched, it is stationary, still the satellite is moving, the satellite is getting that velocity. For example, if you are traveling by bus, you are sitting inside the bus is moving, or your car is moving, but you are not moving. But ultimately you are moving at the velocity of the car or bus. The same thing, if a satellite is not launched, it is stationary. Since the Earth is rotating at some velocity, the satellite is also rotating at that velocity. So by default, the satellite has gained some velocity, even if it is not launched. This is the point number one. Second point, if I will give an example. Suppose many of you, we are going to different shopping malls. We are going to, we are using escalators. Okay. So sometimes if we are in a hurry, we are stepping down in an escalator and we are in a hurry. So we do not wait for the escalator to reach at that destination. If we are in a hurry, then we step down in the escalator and we reach fast. Correct or not? That means why we reached fast? Escalator is moving at some velocity. Then on the escalator, we moved at some other velocity. So the relative velocity is nothing but the summation of two velocities. One is escalator velocity, another is my velocity. So that is the relative velocity. So that's why we reach fast. And if someone who is just standing on the escalator, he is moving at the velocity of the escalator. Okay. Take another in different way if you think. Suppose escalator is coming from top to bottom. Okay. Assume the scenario that the escalator is coming from top to bottom and you are moving from bottom to top in the same escalator. What will happen? Can you able to reach to the top? If you have to reach to top, then your velocity should be greater than the escalator velocity. And if your velocity and escalator velocity will become same, then your relative position will be stationary. Just imagine the scenario, what happens. Escalator is moving from top to bottom and you are also moving, you are also stepping in the escalator from bottom to top in the reverse direction. Okay, so you try a lot, but you cannot reach to the top position. So you have to, if you want to reach to the top position, then you have to put a lot of energy. You have to increase your velocity. Then only you can reach to the top position. But you think the opposite scenario. Escalator is moving from top to bottom, and you are also moving from top to bottom. If you want to reach faster, then you don't stand on the escalator, you also step down in the escalator. So escalator is moving, you are also moving. So the relative velocity will be higher. So you will reach in the destination faster. And you don't have to lose much and require much energy. That is what happens here. The Earth is rotating. Even when the satellite is not launched, it has the velocity that is same as the velocity of the Earth. Now, if we launch the same direction in which the Earth is rotating, then we will be requiring less amount of fuel or less amount of energy to get a certain velocity. Okay, so that is why the satellites are launched towards eastern direction or to eastward direction. Okay, so this is the thing which I said, why launch sites are always on east coast of a sea or ocean, and launching are always in easterly direction. And the answer is Earth rotates from west to east. So incremental velocity required for eastward launch is less than the other direction of launch. Thus, good amount of fuel can be saved. Okay. So it's a very question now. Find the incremental velocity required for a eastward launch to place a satellite at 560 kilometer orbit and percentage of fuel saved for this purpose. I want to launch a satellite in easterly direction, and the satellite will be placed at an orbit of 560 kilometer, which is above the surface of the Earth. And we have to answer that how much amount of fuel we have saved by launching the satellite in the easterly direction. Okay. So first of all, we have to use the third law of Kepler. Oh yeah, this is what I have found. Velocity of Earth's surface. This is 2 pi r. So this represents the radius of the Earth, which is 6,378 kilometers. And I told you we remember these values. Okay, nobody is going to give you the what is the radius of the Earth. These are the fundamental values you should remember. 6,378 kilometers. So this is what this represents 2 pi into r. Circumference of the Earth divided by the time taken by the Earth to complete 360-degree rotation. Okay, so this is called one sidereal day. We discussed two kind of day. One is called the solar day, another is the sidereal day. So solar day represents 24 hours, but the sidereal day is not 24 hours, it is 23 hours, 56 minutes, 4 seconds. If you convert that value into second, so it will be 86,164 seconds. So this ratio you will get as a unit of kilometer per second. So the velocity of the Earth is 0.465 kilometer per second. Okay, so this is the velocity at which the Earth is rotating. Not only Earth, since we are also on the surface of the Earth, so even if my house is stationary, my house is also moving at this velocity. Then let us find what is the velocity required to launch the satellite. The velocity vector is towards east. So since the Earth is rotating towards east, so this velocity is towards east direction. Satellite is to be placed in 5 kilometer circular orbit. Okay, so that means what is the this relationship is what? This is from the third law of Kepler. if you remember the laws of Kepler, so we have the velocity is equal to square root of mu divided by r. This is for circular orbit. For elliptical orbit, we also have noted the expression of velocity. Mu is a constant whose values is 398600. So you remember the value of mu divided by r. So r is the radius of the orbit. We are launching the satellite at an 560-kilometer orbit. So 560 km means from the surface of the earth, it will be 560. That means from the center of the earth, how much it will be? You have to add the radius of the earth. So radius of the earth plus the distance from the surface of the earth. So that is the orbital radius or orbital height of the satellite when we launch the satellite at this particular orbit. So in this way, we can calculate the velocity. So we need this much velocity. We need this much velocity to launch the satellite in an orbit which is at 560 km altitude. So this is the required velocity. But by default, even if the satellite is not launched, the satellite is moving at this velocity. Okay. So what is the additional velocity the satellite require? You just subtract this. Getting my point? I explain it again. Even when to launch the satellite into that orbit, the required velocity is this much. Okay. The required velocity to launch the satellite in an orbit of 560 km altitude, the required velocity is 7.579 km per second. So but by default, the satellite is moving at this velocity when it is not launched. So what is the change of velocity? You just subtract this velocity from the required velocity. So that is give us the incremental velocity. Okay, so we need this much velocity to launch the satellite. We do not require this much velocity. We require this velocity because the satellite itself is rotating at this velocity. Okay, now how much fuel is saved? How much fuel we can is saved? How we can calculate the amount of fuel saved? So this is what is the amount of velocity we saved? This is the amount of velocity we saved. Because this is by default, we are getting this velocity because of the earth rotation. So that is the saved velocity. The saved velocity divided by the required velocity. Required velocity is this one in 200. So that percent. So 6% fuel we have saved. So what does mean at the conclusion we get? If suppose the earth is not rotating, assume earth is stationary, and if you want to launch a satellite at an altitude of 560 km, then we have to launch a satellite at a velocity of 7.579 km per second. Then we have to launch the satellite at this velocity. Only when the earth is not rotating, we need this much velocity. Okay, and since the earth is rotating from west to east, so we are saving this much. So 6% amount of fuel is saved by this. Okay, so let us stop our discussion because we have the end of the class. So you can have any question, we can discuss in the next class.